The photoelectric effect experiment was the experiment that basically confirmed the quantum theory of light proposed by Albert Einstein. Basically, it confirmed the fact that light consists of individual discrete photons that carry a quantity of energy that depends on the frequency of oscillation of the light. Now, another experiment that confirmed the quantum theory of light was known as the Compton effect that was conducted by Arthur H. Compton in 1923. So Compton basically directed electromagnetic waves with short wavelength known as X-rays at stationary electrons, and he examined the collisions between those waves and the electrons. Now, he found that incident electromagnetic waves had a slightly shorter wavelength than the waves produced after the collision. So to see exactly what we mean, let's look at the following diagram of the collision taking place between the wave and our electron. So, this is our incoming incident X-ray that has a wavelength given by lambda, shown by the following sinusoidal wave. Now, this is our stationary electron, and when the collision takes place, basically, some of that energy is absorbed by the electron, and the electron moves away at some angle theta with respect to the horizontal axis. Now, the rest of that X-ray essentially is scattered at an angle phi with respect to the horizontal axis. And what Arthur H. Compton found was that the wavelength of the scattered X-ray was slightly larger than the wavelength of the incident X-ray, and this effect became known as the Compton effect. Now, using the conservation of momentum and the conservation of energy, he was able to derive the following equation, which we're going to derive in a future lecture. So, our lambda prime is equal to lambda plus h divided by me, the mass of the electron, multiplied by c, the speed of light, where h is Planck's constant, and this is multiplied by 1 minus cosine of the angle phi. So once again, the angle phi is the angle between the horizontal axis and the scattered X-ray. Our lambda prime is the wavelength of the scattered X-ray, and our lambda is simply the wavelength of our incident X-ray. Now, using this equation, we can also determine a quantity that became known as the Compton shift. So the shift in wavelength is given by, well, the change in wavelength when this takes place is simply given by lambda prime minus lambda. So we place the lambda prime first because that represents the larger wavelength quantity. So remember, when the collision actually takes place, the wavelength of the scattered X-ray is increased compared to the initial wavelength of the incident X-ray. So, if we use this equation and subtract these two quantities, we get the following result. So, this quantity became known as the Compton shift. It represents the shift or change in wavelength that takes place when the X-ray, when the electromagnetic wave hits this electron. So, now, the question is, how exactly did the Compton effect prove, or how did it essentially confirm the quantum theory of light? So first, let's examine what the wave theory of light predicts the results to be for this particular experiment. So basically, the wave theory predicts that no wavelength should take place. And that's because the incoming electromagnetic wave basically causes our electron to oscillate at the same exact frequency as that particular electromagnetic wave. So when that electron re-emits that electromagnetic wave, the frequency of that scattered X-ray should be the same as the frequency of the electron. So that means there is no shift in frequency, and that implies there is no shift in wavelength. Now, this is not what was actually seen when this experiment was conducted by Arthur H. Compton, and that basically confirmed the quantum theory of light, the fact that light consisted of photons. So basically, incoming photon collides with that stationary electron, and that collision basically transfers some of that energy within the photons to that electron. So the electron gains kinetic energy and begins to move with some velocity. Now, the scattered photon now has less energy than before, and because it has less energy, and energy depends on the frequency, less energy means a smaller frequency, and a smaller frequency means a greater wavelength, as per the following formula. So if the frequency decreases, the wavelength will increase, and that's exactly why a change in wavelength takes place, because some of that energy within the photons is transferred to the kinetic energy of that electron, propelling that electron to move with some velocity. Now, let's go back to this equation for just a moment. So let's examine the following ratio, H divided by ME multiplied by C. So this ratio has a specific name, and it's known as the Compton wavelength. That is given by lambda C, where C stands for Compton. So basically, it's the wavelength of that electron that moves away after that collision takes place. Now, if we plug in Planck's constant, the mass of the electron, and the speed of light, and divide, we get the following quantity: 2.43 times 10 to the negative 3 nanometers. So once again, the Compton effect is the change in wavelength, or the change in frequency that takes place when electromagnetic radiation essentially collides with a stationary electron. There is a transfer in energy that takes place, so our scattered X-ray has a larger wavelength and a smaller frequency because it has less energy. And this is known as the Compton effect. And this basically confirmed, or further confirmed, the quantum theory of light, the fact that light consists of photons that carry energy that depends on the frequency of oscillation of that photon.